You see the optimum, so this outcoupling efficiency has some optimum. And in solar cells, we had stacked contribution plot for light absorption. In the OLED context, we have stacked contribution of light outcoupling. So this green area here is light outcoupling for this particular OLED stack. We have, in this case, maximum of 30% light outcoupling. And this very high efficient OLED, this has an EQE of 41%, really high, was achieved by adding a micro lens array on the outer side of the OLED. And moreover, another trick that was investigated here to actually have preferential horizontal orientation. And this horizontal orientation can be double checked with the angular PL measurement, which is shown here. So that's what Balthasar was just showing in the other room. But this Japanese group was measuring angular PL and then doing fits, and you see the dashed green line fits this data and thereby confirms the angular orientation. So this indicates for doing OLED optical modeling, you need to define the layer thicknesses, refractive indices of each layer. You may or may not add a microlens array externally, and you also need to define whether the emitting dipole is more isotropic or more preferentially oriented. And an additional topic I'll briefly discuss is the birefringence. Some layers can be birefringent as well. So yeah, this is typical data for angular characteristics. And the core of the optical model can be summarized here. It's a classical dipole emission model where we represent the excited molecule by a dipole that oscillates nearby, and present is an electrode, and the electrode will reflect some wave back to the dipole, and that leads to a damping. So instead of having this oscillating dipole here, we have also some reflection of the wave that is emitted that damps the dipole itself. And that's the reason why if you have an emission layer close by the electrode, it can affect the oscillation of the dipole. And in some talks 2 days ago, Marcus told you about the Purcell factor. So this quantity, the Purcell factor, has to be calculated in a way and then considered in order to get the lifetime, the dipole lifetime tau, which is different from tau 0, which would be the dipole lifetime in infinite medium. So if the dipole is placed in organic infinite medium, then it's infinite medium has lifetime tau 0, but in the cavity of the OLED it's tau, and you see that the Purcell factor is it has a crucial influence. And Q0 is the quantum efficiency, the quantum yield of the emitter. And then later on we are looking at modes. We can distinguish what light is outcoupled, what is staying in the thin films. And the way to do this is to segment the power by this quantity U, which is the k in plane wave vector component of light divided by the absolute length of the wave vector. And so that's the outcoupling challenge here. Yeah, we have this problem of total internal reflection at glass air interface. We also have total internal reflection at internal interfaces. And then instead, if we use a macro lens, we can outcouple more light because we don't have internal reflection. There are typical numbers for these modes shown here, and the actual numbers depend on the details of the thicknesses in the OLED. There's a first maximum of the cavity where you have local maximum there for outcoupling. We call it IOC, but we also have the substrate guided modes, absorption losses guided modes, and evanescently coupled. So this evanescent coupling is parasitic process. We are exciting plasmons in the electrodes, and we would like to suppress. So one way is to just make a bigger distance between the emitter and the absorbing electrodes. In the Setfos software, we distinguish 3 ways of calculating the optics of the OLED. The first way is to do spectral calculation. So we have to select here emission mode and go to spectral. That allows us to just at one viewing angle calculate the emission spectrum. And of course you can also do a sweep, make a sweep over viewing angle. That's the spectral mode. And then if you want to do this mode analysis like in the previous slide, this kind of graph involves a more involved calculation that considers all the internal emission angles and all the loss modes. So this is a slightly longer calculation. And as indicated here, it involves some integration. And so in mode analysis, we calculate the overall modes, but in the dissipated power analysis, we look at the integrand there. So these are the 3 modes. There's 3 ways of calculating. Either we look at the details of dissipated power, or the final result where we integrate different parts of the power that is dissipated. The simplest example is here, like emission spectrum in the spectral mode versus viewing angle. We see that there's a typical shift to shorter wavelengths. That's always the case. Shift to shorter wavelengths for larger viewing angles. In Setfos, we not only have an optical model for the thin films, so this is an example of lots of thin films, but we can also put a thick film anywhere we want or have multiple thick films. In this case, we have a thick glass layer of 700 microns and then an additional color filter of some 0.3 micron thickness. And this color filter, depending on the thickness of the color filter, we have here a simulation. If we increase the thickness of the filter layer, it has an extinction coefficient, so the thicker you make it, the more it will suppress this blue and red components of the emission spectrum, and we remain with the green part of the spectrum here in this case. And this is relevant for display applications because basically all OLED displays have a color filter in there, or at least the LG TVs have this kind of color filters, whereas Samsung has more patterned RGB OLEDs. Dipole location matters. On the one hand, it's a question of cavity. Where is the resonance of cavity? So here the thickness dependence is shown again. We calculate the luminance, but we also can plot the emitted color, at least how it is represented by this beamer here. So it's not the gamut of this beamer is limited, but this is the color, how we calculate it from the calculated spectrum. So by basically varying the ETL and HTL thickness, since we assumed that the emitted dipoles come from about 0.1 relative position away from the cathode, so the relative position of emitter stays the same, and by varying the ETL thickness, we effectively change the thickness of or the distance to the electrode. And the anticipated power analysis is looking at more details of the modes. We can do different scans. As a variable, we can choose, instead of angle, we have this option to use U in plane. Remember, that's the K in plane divided by K. And we also can plot the K in plane itself or the effective refractive index. This is a simple example. This power 1, I think that's the example we may open afterwards. And for such an example, so in this example, the dipole was assumed to be in the polymer layer at position 44% away from this upper interface. And we have metal, semi-infinite metal, semi-infinite glass. So with this calculation, we calculate how much light is emitted into the thick glass substrate and a finite thickness of the ITO electrode. That's very simple OLED structure. And then we see, so there's some advantage of using this variable N effective. It's basically something like internal emission angle theta, the sinus of this multiplied by n, but turns out that you can plot it for larger numbers here. So this quantity 1 here represents all the power that is coupled to the outside into air with refractive index 1, and 1.5 is the refractive index of glass. So it allows us to identify how much power is trapped in the glass substrate. And then between 1.5 index and 2, we have the power that is trapped in the organic thin films. And since the organic thin films have a waveguide property, you also notice these sharp peaks here, which are the waveguide modes of the organic films. And then finally, the last peak is, so the organic material was assumed to have refractive index 2, and the last peak is a plasmon excitation that would then depend on how much evanescent coupling we have. And that is actually shown in this example, where same OLED structure, but once the dipole is located far away from, or no, not so far away from the electrode, and in this OLED structure, the dipole is located at the ITO polymer interface, and then the difference in the dissipated power is in fact that this plasmonic coupling here is much reduced as you move away the dipole from the electrode. And basically, taking proper integration over different modes leads us to these contributions here, outcoupled guided mode, and so on. So maybe that's a good point to do some simple OLED exercise, optical simulation with Setfos. So Sandra will again maybe do the first one from scratch or from...
I think since everyone was here before, I think it's not necessary. So what you can open is here is called PLED.par. So what we have in this example is top glass layer. So at the moment we don't have air. So what we would calculate is the emission spectrum into glass, and also the power and so on. And then we have ITO, PDOT, MEH, PPV, calcium, aluminium, and then air. So, and here this is now the emission module. And what you need to define as well for an emission calculation is the emitter position and which layer it is emitting. So here it would be MEH PPV, and it has a certain spectrum that you can load into it, and looks like this, so rather simple. And then you have also to define the distribution. So this would be a delta distribution. It's indicated here, also in the layer stack, and it has a certain position. Here it's just in the center, so this is the relative position. And then you could also have dipole orientation, so parallel, perpendicular, isotropic, or custom, to give any number. Okay. And there was a sweep, which I didn't see. Okay, just take out the sweeps first. Or maybe just sweep the dipole position. It's maybe interesting. Okay, and then you see that the radiance changes as a function of dipole position. So does also the luminance and the efficiency. And in the spectral, you will then see the emission as a function of position. So if we sweep it, we will see that there is a shift of the emission to shorter wavelengths, the closer the emission to the cathode. And you also have it in S polarized and P polarized. But since we are looking in forward direction at 0 degrees here, it's not different. Okay. Yeah, and here is the, well, here would be the emitted color, and the CIE color diagram, our emission would be located here, kind of. Okay. So now we could also vary the angle instead. So instead of having a dipole position sweep, we add another sweep, which is called angle. And we vary from 0 to 85 in degrees of 5 degrees. Steps of 5. There is quenching. Okay, so this is now the trend over viewing angle. You see that it shifts, and to look at the spectrum again, you see here you get a bit an error spectrum, and then it's blue shifting for larger viewing angles. And the radiance would look like this. So this would be something that we could measure with Philos, S polarized and P polarized radiance. Okay. So this is this spectral mode here. For dissipated power, we will open another one. So it's called DisPow 1. It's even simpler. And here you see that we are now sweeping this U in plane. We could also switch to N effect if it's just a normalization. Or, yeah. Not sure if I should show this. I mean, you already showed it kind of, right?
Yeah.
So you have here this spectrum, or actually this one that Beat already showed in the dipole radiation. And here would be also another output, is that you can have some radiation to the bottom, not only to the top. This is what you can see here.
And the waveguide mode is split into S and P waveguide mode, or TETM modes, or two distinct peaks there.
Okay, so now we have, yes, so in this dipole radiation we can keep these two. And now we just move, instead of, we move a bit closer to the ITO interface, so we go to 0.2 and run the simulation again. And then you can see what Beat already showed before. You have a decrease of this plasmon peak and certain improvement maybe in forward direction, so here, but not too much. Okay. Yes, as a next step we could, here we have a parallel dipole, so this is completely parallel to the layer structure, so would be actually preferential. If we now go to perpendicular, we have to keep the old results, otherwise we cannot compare it. Maybe unkeep this. We would now expect, and we see it, if we have perpendicular dipoles, we have much less actually outcoupled to air, or we have much more into this plasmon resonance, of much more power of the dipole, yes. And maybe here, just to complete this, we could also choose isotropic, and then you would expect something in between. Yes, so this is parallel, this is isotropic, and then here's perpendicular. Okay. So what mode analysis does now is just to integrate from actually this dipole radiation plot from certain limits to certain limits, and then splits this up into like outcoupled light, substrate guided, and so on. So to do this, we open mode analysis 1. Oh no, it's called contrib 1. It's a mode analysis, and apart from that, it's sweeping the emitter position. And to speed it up a bit, I would go to steps of 0.1, because it takes quite a while to do this. We have again perfectly horizontal emitters. And here you can now see these modes, so it's actually now doing dissipated power analysis and then integrates from 0 to specific values, and for example to the first integration would give the outcoupled light that you can see here in this IOC. And what you can see here is that the outcoupling is best if you have a dipole position of around 0.2. And then here, when you go to closer to the cathode, you have a lot of evanescent coupling. So you lose a lot and you don't have any radiation. Okay, so this is now for a quantum efficiency of 1. And things change slightly if you change this quantum efficiency. So we change it now to 0.75. So this, you could, as a first estimate, use the quantum efficiency that you get from quantum yield measurements. And you see that we now have also so-called non-radiative losses. And this is just what you lose because you don't have a quantum efficiency of 1. But the peak, so the best position would still be around 0.2 away from the anode. Okay. One example, I don't know if Balthasar, did you show a dipole orientation fit? Okay, so maybe I can show you how we can do it in Setfos. So it's called dipole orientation.par. So we have here mimicked organic film with air at the top. And since we use this hemispherical lens, we have a top glass or here quartz lens. Then we have actually here a very broad emission, so we just assume that the whole film, since it's not so large or not so thick, we assume that it's homogeneously emitting. We could also assume, which would be a bit more correct, I guess, it's an exponential decay at the side where we excite with the UV diode. But this was taken from literature, so it's not measured with Philos. And then we have to go, so here the optimize is enabled, we have to go to the optimize settings. And this would now be our target. So the P radiance is what we measured. Or actually we took it here from this paper. They measured radiance as a function of angle, PL radiance, and just P polarized. That's why it's here called P radiance. This is the target. And additionally, well, it recognizes it already itself, but there is a sweep over the angle, what you could already see here. So there is a sweep over the angle. And in the parameters, we just fit the dipole orientation, which is the main factor, but we also have to do a scaling of the absolute quantity, so that's why we also have a target that is called emission intensity, but it does nothing else than just scaling the absolute numbers. Okay, and then it's actually really fast, so what you would get here is an emitter orientation of 0.31, so it's almost isotropic. And then in the radiance, you have our target, which are these pink points. This is what we loaded into Setfos, and the fit is what you see as a green line. And you can see that it fits quite nicely. What we could recommend from our experimental observations is that you would also, at the same time, also fit the as polarized radiance, because then you can trust these results a bit more. But typically in papers they only report a p polarization, so this is also what we can do here. Yeah, and then you have some optimization, like parameter evolution and so on. It's more numerics. Okay. Then this was purely emission, so now we will go to also including scattering. So the first example would be me scattering. It's called scattering me. So here we have a stack, HTL, ETL, ITO, and then on top of that we have a scattering foil or something, so which aims to actually it's in between ITO and glass, so we hope to outcouple also the modes that would be lost in glass otherwise. So yeah, I should also talk. So you go to this arrow of this scattering layer, and then not in the material but in the scattering tab you see that we have particles, and that we untap now the non-random seeds, and they are monodispersed, so we just have one size. They are me kind, and we have certain radius, certain concentration. This is volume concentration, and a refractive index of the file, so of the particles. Here you could also load a file, and you can also select more than one particle, polydisperse or Gaussian distribution. Yes. And now you see that we also have again emission plus scattering module enabled, and yes, at the same time we sweep the concentration of these particles to see the effect. So in the integrated luminance you can, or in the integrated radiance, whatever you prefer, you can see the effect of the scattering particles. So if we have a low amount, we have less integrated luminance. So integrated luminance means over the full hemisphere now, because we are using 3D ray tracing. We have scattering, we have the integration over the whole hemisphere directly. And what else do we have here? Yes, also this would be not integrated, but angular resolved. So you see that in forward we win a bit, quite a bit actually in luminance compared to concentrations which are low or negligible even. But also it saturates kind of, so there is a certain point where you don't win anymore anything.
And at a certain point you even have backscattering if you have too many particles in the film. Yeah.
Yeah. Okay. Since I think last version, right, you can couple it also to the mode analysis. So you can look at the or outcoupled light intensity, so these modes, remember from before, when you have such kind of particles or other scattering events. Actually, we look now at an example where we have hemisphere or micro lenses. So it's scattering OLED mode. And here we have not a layer that has scattering particles, but we have this micro lens interface, which has certain dimensions, and we also disable this non-random seed. And here would be the number of rays. So if we want to speed up and lose a bit of precision, we can decrease the number of rays. And apart from that, yeah, it's I think the same OLED as before. And here we also reduce. So in the scattering tab, we can also reduce a bit the angles. There is always so much. Oh yeah. So whenever you have ray tracing, you can click on this 3D icon, and then you see the output of ray tracing directly. So these are the incident rays in blue and the scattered rays in green. Then you can rotate and look at your hemispheres.
But for this visualization, only a few rays are drawn, not all the 100,000. Just to give an idea how the rays are. Blue is incident from below, and green is scattered through. Yeah.
Okay. Yes. So since we have now this micro lenses here on top of glass, we have the chance to also outcouple the glass modes, and this is what you can see here. We have a lot of outcoupling now. So typically for flat glass, you have around 20%, and here you have around 46% if you use this micro lens array. And I'm not sure if there is something in, yeah. Texture. Yes. Yeah, these are just the normal mode analysis outputs. So you have the relative contributions. So this is this, but not stacked. Sorry, here. And here wavelengths resolved, and dipole lifetime. So yeah, I think there is nothing else to show. Yes, I think you can. If you have parameterized hemispheres, you can optimize this. I would need to double check whether it's possible, but I think so. Do you know? Can we optimize these parameters directly?
Yes, the geometry parameters can directly be optimized. So you can sweep the lens parameters and also the OLED stack parameters, and that's one of the key advantages. Instead of optimizing the stack separately from the scatter foil, or that you can simultaneously sweep scattering parameters and stack parameters. I think you could, probably you would find if you do a sweep or optimize, it's always the parameter you want to. Here's a pull-down menu of all the model parameters you can sweep or optimize. And optical, I think we have, don't remember exactly where we find the dimension, the parameters of the, I'm not prepared, but I know it's possible because we have some. I mean, the previous example of me particle scattering, we could vary the concentration. Similarly, you could also vary the lens diameter of the micro lenses.
Yeah, I think that's it for the optics.
Mhm.
Or if you have, I will find out in the meantime when he's talking how it's done. Otherwise, we can continue with.
Yeah. Example, I think it was maybe even the same example that you demoed.
I
Or?
didn't show the birefringence. Yes.
Yeah, but in this particular example that Sandra showed before, the imported reference data from this other publication, the fit, in this case, the dyes are dispersed in a matrix material, and the matrix material itself has some preferential orientation, so optical anisotropy, and this birefringence can be considered in the model by entering an optical refractive index NO for ordinary and extraordinary light propagation there in this layer. So this is a optical property that you would have to measure with an ellipsometer and then import this. And birefringency can actually also help to improve the outcoupling overall. If you have a stack, in this example, the refractive indices of the organic layers, ETL, EML, ETL, these three layers, all of them have 1.7 as a refractive index, but now we can choose the O and the ordinary and extraordinary refractive index. They can be the same, so then basically isotropic. Then we would have an outcoupling efficiency of 54%, but if we then introduce birefringence by setting either the ETL extraordinary refractive index, this is the case, we put the HDL and E down to 1.3 instead of 1.7, then we end up with 55%. And if we also reduce the extraordinary refractive index of the ETL, then we move down to this point here, which is 74%. So we have dramatically increased light outcoupling efficiency from 54% to 74%. And that's really matters, right? So that's why people are trying to exploit birefringence materials in the OLED stack, in addition to optimizing or planarizing the dipole orientation. And in another example from the literature, one of our customers actually modeled or optimized the OLED stack to get very high efficiency TADF OLEDs by introducing low index ETL. So instead of using a bilayer electron transport layer system, they replaced it by a single layer which has a lower refractive index. It's not somewhat lower, 1.65 rather than 1.75 or 1.8, and they could show by the simulation that this dissipated power for the evanescent coupling into surface plasmons is much reduced as you decrease the refractive index of the ETL from 2 down to 1.5. You see, you can suppress the evanescent mode, and that was then the reason why they got a much enhanced outcoupling or EQE efficiency of their OLED by introducing the low index ETL. So they did similar mode analysis. In view of time, I don't go much into detail of the further optics examples, but this is the direct comparison of the example that Sandra was showing before, where a similar 3-layer OLED was taken, and in this planar configuration, if we just look at glass, planar glass, then we would have only 21% light outcoupling into air and 32% trapped in the glass substrate. But by adding this micro lens array on top of the glass, we increase the air mode up to 38%. So that's almost doubling the light output just by adding the micro lens array. And that's the reason why for OLED lighting applications, you could just simply laminate an external micro lens array. Yeah, but the guided modes and the evanescent coupled is still the same, but due to the light scattering, you also increase the absorption losses, because light will bounce back and forth a lot more, and then you also have more absorption losses. And so this is a summary slide of the optics workflow. In case you have more than planar layers, you also have light scattering. In our software, we have several ways to introduce scattering of light. You saw micro lenses, so that's kind of a texture. You saw particle scattering, and we also have several ways how to calculate scattering behavior. For a given texture, for instance, or a given particle scattering, we calculate bidirectional scattering distribution functions, which can be tabulated this way with an intensity map. For any incident angle, we can specify how much light do we have at any outgoing angle, and then this is considered locally for the scattering interface, and then we do the overall calculation of internal light emission and external light emission, and in the end we have a spectrum that we resolve versus viewing angle. And quite often, by introducing scattering in the OLED, we can get rid of angular dependence, so the spectrum is more stable with viewing angle, and also it's more diffuse, more broader in terms of angle. Okay, that concludes the optics part. If you have any question about optics, meanwhile I'll open the electrical modeling part. And so this is kind of a summary about, here we have a presentation about electrical modeling. We distinguish between electronic part of the model and the excitonic part of the model. This is a reminder of how the software is divided into 4 modules. So for electrical simulation, we would use this Drift-Diffusion Module. And for fully coupled electro-optical modeling of OLEDs, we could couple drift diffusion together with emission and also with light scattering. So these 3 modules can be combined in Setfos. So I have way too many slides, so I hope you don't mind if I do some skipping, because we don't have that much time. Drift diffusion model first, and then we have I will go through some modeling ingredients, and there's also some examples about exciton dynamics. So that's just the operation of the OLED you're familiar with. We have charge injection, transport, and emission coming from excitons that are generated in the EML. So the exciton parameters would only be specified for the emitter layer, and the neighboring layers do not have excitons in the model. Basically the software is divided, so we can choose to just do optical calculation as just before now, and or we can do charge drift diffusion calculation, and then the recombination process will generate an exciton, and the exciton can diffuse, transfer its energy to guest molecules optionally, and then decay. So this is all happening simultaneously: exciton migration and transfer to guest molecules and optical decay. And the optical decay is then solved by the optical model here. And around everything we can also use sweeping or optimization, and also fitting. So we can fit IV curves, or we can fit emission spectra that you feed. There's some more details of the model. Standard drift diffusion model shown in the green box. And for the excitons, we kind of have a generic, bit phenomenological exciton continuity equation, where we can have a generation term. That's, in this case, that would represent the recombination happening between electrons and the holes here. And this recombination term is a sink in the charge continuity, and a source term for the exciton continuity equation. And for the optical model, we consider the radiative rate here, K rad, that's coming from the optical part of the model. And K non-rad is just a material parameter that you enter. And there are some additional processes allowed, like exciton annihilation, also exciton polaron quenching, which is not shown on this example here. And also energy transfer from host exciton to guest exciton, which is simply from J to I or from I to J. We can transfer energy. So we can couple several exciton equations. You can have several excitons in the same emission layer, for instance. And we can solve all these equations in DC, transient, and AC state. One interesting quantity is the charge balance. It's always nice to keep in mind that we have hole injection, electron injection. Some of the charges are consumed by recombination processes, and the charge balance factor can be expressed, and it's also plotted in this profile. In the steady state, you will have a current density, which is simply the sum of electron current and hole current, and you see that these carriers are consumed in this emission layer. This would represent alpha and PD as a host, and the guest molecule would be placed here. And in this case, we have ideal balance. All the carriers are consumed in the emission layer, which means recombination efficiency expressed like this is going to be 1. And the other name for this is current balance. That's always an interesting thing to evaluate. An overview about the parameters needed for electrical modeling. Of course, we need for each layer homo-lumo energy values, layer thicknesses, work functions of the electrodes, and then also mobility parameters for electrons and holes. Optional doping. Some layers could be have charge doping. You can also introduce traps for electrons and holes, and you can also introduce dye dopants here, and the dye dopants are basically taking the energy from the host excitons and then re-emit the light that we want. And in the end, you get the current voltage curves, quantities that you could measure in the lab, but you also get quantities that you cannot measure in the lab, namely cross-sectional profiles of charge carrier densities or energy band diagrams and so on. And in this example, it's quite a typical 3-layer device where you have a barrier for electrons that came from the cathode. They would be piling up here, shown in red here, and the holes come from the anode side on the left. They would probably pile up at this interface. That's why we have a blue peak there. And it turns out that quite often you would get a split emission zone where you have high recombination on both sides of the emitting layer. This was also studied experimentally by Marcus, who presented 2 days ago. Yeah, and I think I will jump a bit further. Of course, you could consider, instead of single energy level for homo-lumo, you could also introduce disorder, because these organic materials are amorphous and disordered. Then one option is to use EGDM as a disorder model, where not only the density of states is modified, but also the diffusion coefficient is replaced by an expression that is density dependent. But you can also, for instance, describe this disorder by sharp energy level and some trapped charge carriers here to kind of mimic this tail here for this whole transport in the HOMO. And this is what Evelyn has done in a previous study, and this illustrates that charge transport now described by a voltage step characterization. We apply voltage step and measure or simulate the current. This is simulation. If we don't have any charge traps, you get a nice transit time peak, which is related to the mobility of the hole carriers, and you get a constant current very soon after this transit time. And this is a plot in log time scale. But then we can introduce charge trapping. Either we can have very fast traps with a high capture rate, then what you notice is that the transit time is delayed due to trapping, the arrival time is later, and we get an overall current that is reduced by this fraction theta, which is simply the fraction of free carriers to total carriers. But in some intermediate case where a capture rate is not as high, then you will have charge trapping happening over very long time scales, and the current will still decrease after a very long time, as you can see here. So that's if you ever have a measurement that doesn't settle to a steady state value, maybe it's due to trapping, and that's what this example illustrates. And in terms of charge recombination, the standard Langevin recombination is implemented, where you have a recombination rate that depends on electron hole density and the sum of the electron hole mobilities. But we also have implemented Schottky-Reed-Hall recombination, which is an additional process where we are generating electron traps, or we're filling electron traps. So this electron from the LUMO will be captured in the trap with this first term here. And when the trap is filled, we cannot capture anymore. So that's the reason why we have this difference. And then in a later time, maybe there's a hole walking by from the HOMO, and this hole P can then be trapped by the it can recombine with the trapped electron, and that's this expression here. So that's the Schottky-Reed-Hall recombination effect, which can be activated in the model as well. And it's possible that a dye molecule that is doped into the emitter layer will act as such a trap where, the user can choose this. And this kind of trapping is relevant also for solar cells, highly relevant. In dark JV, you can see that if you allow for Schottky-Reed-Hall recombination, then the reverse current in the dark is much higher than without this process. Okay, about hopping model and interface modeling, I presented yesterday. Maybe afterwards you can look at an example. Impedance simulation is also an interesting method, as we have seen during this conference. We can calculate the impedance and plot it in different ways. One way to plot it is the cold plot with the real and imaginary part. In organic semiconductor, it's typical to see a kink here in the big circle, and this kink in the big circle is due to the transit time, depending on the mobility of the carrier. At this characteristic frequency, the inverse of the transit time, we have a kink here. That's space charge limited effect. Then if we would introduce trapping, we can also get an additional semicircle at the low frequency side of this whole curve. And interestingly, if you would add self-heating, and I have to say that in Setfos, we do not consider self-heating yet, but Evelyn Knapp was publishing this nice study where an additional heat equation was solved consistently together with the drift-diffusion equations, and then you can even get negative capacitance, or in this representation, a positive semicircle. But this next example is one that maybe you can open afterwards in the exercise. It's just a basic example, a single layer organic semiconductor device, where we have a single layer and the two electrodes have different work functions. So we have a peak in the capacitance, slightly not at 0, but a bit maybe at 1 volt. So it means that it's not a symmetric device, and we are injecting carriers at this voltage where we see a peak in the capacitance, but in the negative bias we would have the geometrical capacitance, and that is visible here in the charge density plot if we have the charge density versus voltage and position. In the reverse bias, we have very little charges, so it's fully depleted in the reverse bias, but in the forward bias, we have injection of charge carriers. And so this is an example that besides simulating curves that you could measure, you can also get inside view in profiles in the device. Carrier profiles, field profiles, band diagrams. And there's a section in this presentation where we discuss a bit more the excitonics, TDF emitter molecules, or TDF OLEDs are a hot topic. Here we implemented, we have an example. What we implemented is having a transfer rate, intersystem transfer rate. We call it KT because we're populating the triplet state, but we also have a back transfer, which is the reverse intersystem crossing. We call it KS, back to the singlet. And while one of them is a constant, the other one is a temperature-activated process. So if we would run a temperature-dependent simulation, the transfer rate is increased at higher temperatures. And we have made some demo simulations where we simplified. We only have the arrows, but not the dashed arrows. So this state here does not emit light, and so we have some simplifications here. And this simulation example has these choices of parameters, the radiative rate, and then the conversion, the reverse intersystem conversion rate. That's the simple thermal activation we assume in the model, and the user has to choose delta E, is energy splitting between the triplet state and the singlet state. That's delta E. And you can imagine that these two processes are happening simultaneously, and in the end, for a simple model, there's also even an analytical solution in the steady state. The internal quantum efficiency can be expressed by these fractions phi t and phi s, and we can double check our model implementation with this reference solution, which is this dashed line is the analytical model, and the dots here are simulation. So we varied the temperature of the device and repeated the simulation for each temperature. And you can imagine that this balance, the population of singlet and triplet states, depends on temperature because the reverse intersystem crossing is temperature dependent. So this behaves well. And then we can also play around and do, instead of a steady state simulation, do a transient simulation. In the transient simulation, we turn on the voltage and earlier on, but now we turn off the voltage at this position, and we have a fast decay and a slow decay. And the slow decay is due to the conversion process of triplets back to singlets, and the fast component is the direct fluorescence. And we can also double check if the slopes that we get from the simulation with Setfos agrees with what you would expect from an analytical model. And that's shown here as dashed line is the analytical model for these two time constants, gamma 1, gamma 2. So this is all making sense. And you can repeat this pulsed simulation at different temperatures, and you see that the slopes of the delayed component changes significantly with the temperature of the device. So this is well behaved. And then there is some more things about the dynamics of charge carriers. Turning off the device can sometimes lead to an overshoot, which was also measured by the Theodrestin group, an overshoot in EL intensity after you turn off the voltage. You can have an overshoot. And in the simulation, we can also observe this. And thanks to the simulation, we can confirm some hypothetical picture in that old publication that indeed we have excess charge carriers accumulating at either side of the EML. We see here we have a lot of carriers because the quasi-Fermi level is close to the LUMO, and here we have a lot of holes because the quasi-Fermi level is close there. And then when you turn off, so this is the on state. If we have a constant forward voltage, this would be the steady state in the on state. And now that we would turn off, so 5 volt forward bias, now that we turn off to 0 volt, 0 volt means that the quasi-Fermi levels are aligned here on the right and on the left. And now the field has changed. In the forward, the slope of this band diagram was like this. And now in the reverse bias, the slope is the other way around. And that means that the electrons that have piled up on the left, they want to go down this diagram and back to the cathode, and the holes go back in the other direction. And because of this extraction of carriers, all these holes that are on the left now, as a function of time, they will be extracted to the right, and these go back to, the holes go back to the anode. And that will lead to recombination, a delayed recombination that indeed can lead to this emission. And because this calculation can be done fully coupled electro-optically, we can even simulate the spectra versus time. This would be the transient electroluminescence spectra versus time here, and that's the integral of the luminance, the luminance versus time. Okay, but this particular study was done in detail by Marcus, who published this paper that is online since a few days, and there you see how he measured for a phosphorescent OLED, how he measured this delayed overshoot, and how he simulated and explained it by the Setfos simulation. But I think in view of time I will advance. So here are some examples of additional exciton processes. So the purely radiative part is simply a K radiation, K rat or K total, and then multiplied by N, but we have added additional processes, triplet annihilation, TPQ as well. One goes with the square of the exciton density, another one goes linear in the exciton density but couples to the charge density. So in the end you have sometimes get a exponential slope but also a non-exponential slope, and the tricky part is to identify by comparing with a particular experiment, identify the relevant mechanism. We also implemented some saturation effect. Sometimes if you have a host-guest system, the host exciton would transfer its energy to the guest, but if the guest is already fully occupied, no more relaxed guest molecule to accept energy transfer, then you end up with more emission from the host, and that is shown on the right-hand side. If you increase the voltage, you may end up saturating the guest molecules and having a change in the emission spectrum due to the population of the host. So in the end, this is the summary of the phenomenological exciton rate equation that you find in the manual. At least that's from version 4.5. We have lots of terms here that the user can turn on or turn off. You see some of them labeled here: TADF processes, annihilation, triplet polaron quenching. And some are more relevant for the solar cell operation, but we kind of have a generic equation that is useful for solar cell as well as for OLEDs. Yes, I think with this I can take some questions, and we could then start these exercises.
Still awake?
If we still, yes. It has been a long day, I know, and maybe some of us need a coffee break and drink, but I'm afraid there's no more buffet outside. At least we didn't order one, but...
Okay, it will not take so long, I promise.
And I have to apologize, I need to be somewhere at 5, so I will leave soon, but Sandra may be happy to to stay around.
So the example is full OLED. Full OLED.par. Since you've been here quite some time, I think I don't have to explain all the details. So the only thing we add now is to couple the emission to the charge distribution. So this is done here. So before we had delta emitters or exponential or Gaussian or file, and now we just couple it to the excitons. And to define the exciton parameters, you can again go into this material file. And then you see it's the really basic example, just one exciton with a certain radiative rate and non-radiative rate. It seems to be a singlet exciton, so it's generated with 25%, and there is some diffusion. And here would be all the other parameters like exciton, polar, and quenching, and so on. And then again, there is a sweep that I think we don't need at the moment. Yes, we switch off the sweep for the moment because it's just an angular sweep. So then you have again band diagrams. You also have now additionally like recombination profiles. So you have more recombination at the ETL interface, and you have now also excitons because you couple from the recombination directly to the excitons, and this would be the exciton profile then. And then you of course have also some spectral data, so this would just be the emission, and there is also normalized emission and white emission. So white emission just ignores your file that you give in here and just assumes a homogeneous emission throughout the whole wavelength range. Okay. The next one would be a multi-layer OLED. So this one is called full OLED white. So you see all the names that start with full or electro-optically coupled. Here. So you see that we have a lot of layers here now. And we have actually not only one emitter, but we have 3 emitters. So we have one in the TCTA ERP layer, one in MPB, and one in Spiro, blah, blah, blah. And all of them are, again, coupled to excitons. Actually, they are coupled to the same exciton, so we use the same exciton parameters. And additionally, I think there are some traps, but it's easier to run it, because then I can see where they are. Otherwise, I have to click through all the layers. So in the charge density plots, yes, you see that we have also introduced some electron traps in this Spiro DPVBI layer, and here you would see the occupation of these traps. Okay, what could also be interesting is, again, the recombination, and the exciton density is now having non-zero value in 3 layers, so you have 3 different colors. And spectrally, you should also see that, yes, by having an overlap of these 3 emission spectrum that actually are like here. So here we have a green one, and here we have something red, and finally also something blue. And if the resulting fully electro-optically coupled simulation has then the 3 contributions. And depending on the charge mobility, you have more or less of one of the other. Okay. Any questions here? No? Okay. Then you can also do a sweep. So we will sweep the voltage, so to get an IV curve. Just 0 to 10 volts in steps of 1 to speed up. Yes, okay. Now you see that, well, I think I will look into the normalized emission. Yes, and then you can see that there is, depending on the voltage that you use, that you apply, you have a shift of the spectrum. So the higher you go, the more red contribution you get. And this you could now understand by looking at the charge densities as a function of voltage. So yeah. So it also works for such complicated structures which have a lot of layers and a lot of barriers, but of course there can also be problems with convergency. Okay, so now we always looked at or steady state, and we now want to look at transient. So here in the drift diffusion mode, we will look at, no, actually AC, so not transient. To do this, we will open an impedance.par example, because with so many layers, I'm not sure if it will work. So what we do here is to sweep the frequency from 10 to 1e10 hertz, yes. And it's a very simple structure, not even, well, it's a hole-only device. And yeah, this is actually the only thing you need to consider. And then what you can see is charge density, and what you also have now is so-called oscillating charge density. So for lower frequencies, you have some pileup of charges here, or no, actually for higher frequencies, you have some pileup of charges here, and then they somehow penetrate a bit into your layer. But this is a really basic example of just a hole-only device with two ohmic contacts. I think the one that Beat showed is actually called impedance IV. So this is this would be just at 1 voltage. Actually, this is 0.5 volt. So to generate the capacitance frequency plot, we need to vary also the voltage, and this is what is done here in these sweep settings. Again, and we just look now at one frequency and look at the same device. And then you can look first at the capacitance, and you see this geometrical capacitance value, STLC, and this peak that Beat showed already. And again, the interesting thing is then the hole density, where you can see that here the device is depleted, and you get above, well, 0 or a bit more volt, you get a lot of charges in your device. Okay. Almost there. Like that's before we finish, we have also a TRDF example. It's called full OLED TRDF. And the interesting thing now is to look at the excitons. But I have to find. Ah, yes. Okay. It's in the alpha NPD layer. Well, yes. So the emitter is in the alpha NPD, and here we have excitons, and actually only exciton 1 is emitting. So it seems exciton 1 seems to be the singlet emitter. But we have here in this material file, we have also a second exciton, which would be the triplet emitter. So you can see it's generated with a percentage of 75%, and exciton 1 is generated with a probability of 25%. And this one has a radiative recombination rate, whereas this one has no radiative recombination rate. And what is now the the interesting thing is this prefactor, so you have this transfer from exciton 1 to exciton 2, which would be the intersystem crossing rate, and you have the reverse intersystem crossing rate here with the prefactor and this distance between the energy levels. Okay, and I think there is now a sweep over temperature. Yes, so to see this effect of TIDF, we have a sweep over temperature and look at the internal quantum efficiency, which should increase due to higher temperatures because of more reverse intersystem crossing. So, well, you see it also in the current efficiency, though the higher you get, the more efficient you are. Of course, this is also in the luminance and the radiance. Here is the internal quantum efficiency, yes. It's the same trend. Okay, any questions? Or no? And last example I want to show here is the Hudson interface. So if there is someone interested in this material or in similar material, it's called Hudson injection. Actually, it's only electrical, but one could also couple it then to emission, of course. This is just to look at the electrical charge profiles. So here you see this band diagram of such a Hudson device, and then you have to introduce this new interface model at this interface. This is done here, and again, as for the solar cell, we just have to select a hopping frequency for this interface. And yeah, apart from that, there is nothing special. We just look at the operation of 6 volt of such an OLED. And then in the charge densities, you can see what you hopefully already saw yesterday, is that you have in this Hudson layer a lot of electrons actually, and they are piling up at this interface, and on the other side you have the compensating hole density, which is fed into the OLED, and where it can recombine in the EML together with the electrons from the aluminium. So the recombination is still actually in the EML where you expect it. Okay, any questions? Any other examples you want to see? No? Okay. Well, thanks for coming, and please bring back the dongles, and if you have other questions, or we're here to answer them, Simon and Balthasar, Konrad. So, yeah. Thank you for coming and staying.